So I'll be solving problem 4 of test 1, and I chose this problem because I missed the most points on my test on this problem. So the problem statement includes this lovely picture, which I've drawn on the whiteboard, and it says that this rod, which is bent into a semicircular shape, has a distributed charge of negative Q. And our goal of this problem is to determine the electric field at a point on the z-axis. So it's divided into parts, and part A says to consider an infinitesimal slice of the bent rod with an angular length delta theta located at an angle theta from the right end of the rod. So that would be this tiny little slice here. And we're going to find R that points from the center of this slice, so from the center of the slice, meaning right here, to some point Z on the z-axis. So in order to find R, remember it's just R observation minus R source. And our R observation is this point here on the z-axis. So 0, 0, Z. And our R source, it's coming from this point right here. And if you'll remember from polar coordinates, when you have a circle, XY converts to, let me go ahead and write it like this. So minus X, Y, 0. However, when you have polar coordinates, like I was saying, X and Y convert to R cosine theta and R sine theta respectively. So your R is going to be negative R cosine theta, negative R sine theta, and Z. Okay. And that's it. There's your answer. Alright, so part B, that was part A, this is part B. We're going to determine an expression for the charge on the slice delta Q in terms of length delta Q. Okay, so what we're doing is trying to find the charge on this tiny little piece here, defined by d theta. And if you'll recall, the arc length formula is simply S equals R times theta. So that's how I think about these types of problems. The denominator is going to be the total length of the rod, which is just going to be, since this is pi over 2, it will be R, the radius, times pi over 2. And then on top, we'll just be dividing the tiny piece of charge that we get from this infinitesimal slice by the arc length. So it's just negative Q, because that's our distributed charge, times delta theta. Okay. And then, times R delta theta, to find the arc length there. So what we find is that our R's are going to cancel. The 2 is going to flip up to the top, and we're going to get negative 2Q delta theta over pi. Alright. Now I'm going to erase the board real quick so we can move on. Now in part C, we're actually getting to the good stuff. We're going to derive an expression for the vector delta E at 0, 0, Z, which is our observation location here. So we're going to start with just the formula for a point charge, because remember, since it's such a tiny point here, we can approximate that to a point charge. And that is simply E equals 1 over 4 pi E naught times Q over R squared times R hat. And what I did on my test is I forgot to leave out part of this R hat, which is where I lost my points. So we'll make sure we get it right this time. And we know from the previous problem that R vector is equal to negative R cosine theta, negative R sine theta, and Z. And then, so we need to figure out the magnitude so we can plug it in here, and R hat here, so we'll go ahead and do that. Our magnitude is just going to be square root of R cosine squared, R squared cosine squared theta plus r squared sine squared theta plus z squared. We can pull r squared out here and get cosine squared theta plus sine squared theta inside the parenthesis. So this is a trig identity which goes to 1. So we're left with r mag being r squared plus z squared, and then the square root of that. Cool. And so that means r hat, we're just going to take your r and divide it by r magnitude. So we'll get negative r cosine theta, negative r sine theta z over our r mag, r squared plus z squared. Okay. Now we're just going to put everything into the formula. We're ready to go. So delta E is going to equal 1 over 4 pi E naught times Q over r squared, which is going to be the square root r squared plus z squared squared, so that'll just eliminate the square root, leaving us with r squared plus z squared. And then finally times our r hat, which is this. So negative r cosine theta, negative r sine theta z over square root r squared plus z squared. We're going to do a little bit of simplifying here. Oh, we have to plug in Q, which we calculated in part B, to be 2Q delta theta over pi. Negative 2. Okay, so after simplifying all of that, we'll get 1 over 4 pi E naught. Our negative signs here and here are going to cancel. 2Q delta theta over pi. This is r cosine theta, r sine theta z. And then we're getting 3/2 because this is essentially to the 2 over 2 power, and this is to the 1/2 power, so you add them and get 3/2. So here's our answer. Sorry, it's messy. Okay, that's all part C. I'm going to go ahead and erase the board. And the last part, of course, wants us to integrate. We're going to use our formula for E that we just derived and integrate from 0 to pi over 2. Oh, and it did say integrate to determine the z component. So we're going to, instead of doing the negative r sine theta, negative r cosine theta z, it'll just be the z because we're ignoring the x and y for now. So we're gonna, all of this stuff is constant. Since we're integrating d theta, this is the only thing that'll be left in front of the integral sign. Everything else is gonna get pulled to the left side. So we're left with d theta here, and that's a pretty simple integral to do. D theta just integrates to theta, pi over 2 to 0, plug that in, and you get pi over 2. So we're going to be multiplying all of this that we pulled out times pi over 2. And once we do that, we're going to get this. So our 2's are going to cancel and our pi's will cancel. And our final answer is this. Okay, and that's all. Thank you.